Okay, so let me go back a little bit. So this is the fundamental theorem of calculus of vector fields. Technically, that would be an overstatement because it is only limited to the gradient vector fields. So in a way, as we'll see, this is like a preliminary version. A preliminary version of the theorem of the general theorem of calculus vector fields, because we know that most of the vector fields are not gradient, and so this is very restricted for something that's called the fundamental theorem. So we'll get to that later. So then, furthermore, this topic that I kind of abandoned, but shouldn't have, it is the path independence versus gradient vector fields. So as we have discovered that well, the definition of path independence is pretty much in this picture. Okay, so it doesn't matter which path you take from A to B, you're going to have the same integral, same work, same. Okay, so that's why, and it is true for gradient vector fields that they are all path independent. This is actually what I erase here. So gradient vector fields are path independent. Okay. So one thing is easy to overlook in the definition that we're talking about every single path. Okay, so in other words, every pair of points A, B in the definition here would produce a bunch of paths between them. Okay, and all of those paths have to be produce the same number, and then we call the vector field path independent. So it covers everything, and that's why it is connected with such a big restriction as being gradient. A gradient of the gradient of a function. Okay, so that one way is very straightforward. Gradient vector field is path independent because why? Because of the conclusion of the fundamental theory, right? So only the beginning and the end points matter. That's right there for gradient vector fields. So now the converse is also true. So, and vice versa. Okay, so let's read it backwards. So if if a vector field is path independent, then it is gradient. Okay, so path independent, gradient. So that's the converse. That needs a proof. Fortunately, the idea is sort of there in Calculus 1, how we prove to begin with is that a vector field is gradient, and we did when we had specific vector fields. We just did algebra to find the potential. So to prove that a vector field is a gradient vector field, find its potential function. Okay, so del f is equal to f capital. Okay, so it is, and then we go back to this analogy, not more than an analogy, but rather generalization of the idea of derivative and derivative. So this is written in a more traditional way. F prime is equal to f uppercase. So we are looking. So f is given. Okay, so given, and we're supposed to find f lowercase. Okay, so in other words, we are talking about literally anti-differentiation or integration. That's the way we certainly would call it in Calculus 1. But the idea is the same. So we sort of we have the answer to the question, and now we need to find the question. Okay, so that's what f lowercase is. It is the potential function, and it is the derivative of that is our f capital. So how do we find it? We did it pretty much, well, if you might remember. So do you remember how it was done in Calculus 1? This was, to refresh your memory, this is about Fundamental Theorem of Calculus, Part 1. So remember Part 2, we only mentioned yesterday, it was that the differentiation and anti-differentiation cancel each other. Okay, so that we used yesterday, and it is Part 2. What's Part 1?
Part 1 is that if you integrate the derivative, you get the function?
No, that's Part 2. That's exactly canceling of differentiation in integration. No, it is related to this question, is how do we build antiderivative? Okay, so that's the Part 1. So once again, this is FTC 1 refers to Calculus 1. Unfortunately, the symbols are screwed up, but this is how it goes. F of x is equal to integral from, say, a to x. Does this look familiar? F of t dt. How about that? So this is entirely within the notation of Calculus 1. Does it look familiar? So the idea is that we have the way Calculus 1 develops. You define the Riemann integral as the limit, okay, and so which has nothing to do originally with the differentiation, and then you connect it back with the fundamental theorem. Part 2 we just discussed. And this is Part 1, which literally builds antiderivative from Riemann integral. So you take a Riemann integral. What you would do with it? You change the upper limit. You make the upper limit variable. Okay, so rather than this is the typical situation of the Riemann sum, integral from a to b, it's the area. All right, that's all fine. But then what we do is we don't stop here. We instead let the variable, let the upper limit of the integral vary. So x varies left, right, and so you create a new function. As long as f capital is integrable, then you're fine. Then you create a new function, and then the statement of the fundamental theorem Part 1 is that this is an antiderivative of f capital. In other words, f prime is equal to f uppercase. Okay, so that's exactly what we're after. We know how to do line integration. So back to high-dimensional case. Multi-dimensional case. So we know how to do line integration through Riemann sums, and we use it to build what? To build the potential, f lowercase. And the answer is pretty much the same. This is how. So the formula is almost identical the same, except I will replace x lowercase with x uppercase. So this is still all Calculus 1. This over here, just to refresh your memory. And now we proceed with the Calculus 3, and this is the answer. So once again, f capital, our vector field is given. How do I build a function of say 2, 3, or more variables? From that function, the answer is I integrate a lot, pretty much along every single possible curve. This is how. So f of x capital. So capital X, meaning that we're talking now about points in the multidimensional space, is equal to integral over C, line integral, f dot dp. Okay? So there is no x on the right. Well, I'm sorry. We start with fix point A. Fix point A. And then what you do is you pretty much integrate from point A along every imaginable curve. So these are my axes from A to B, and so how do I find the value of my function f at every x, say x1 and 2 and 3, I integrate along these curves. Okay, so that's the definition, where C is an oriented curve from A to B. Okay? The idea is exactly the same as in Calculus 1, except in Calculus 1 we had only one direction, so that was hidden. the picture was hidden, but otherwise we're using integral to build antiderivative. So that's the fundamental theorem of calculus for you. Now, why does it work? Why does it work? What is the issue that we have to overcome here? As you can see, why it works is because it is path independent. So as you can see on the left, my function f only gives me one point, the endpoint of my path x. Okay. So then on the right, however, the integral is specific to that curve c that we pick. However, we know that if there is another curve ending at the same location x1, the integral will be the same because that is the assumption of our theorem. So we have path-independent vector field, which means that only the endpoints matter. One point is fixed, A, and then the rest of them are don't matter how you get from to the other point, the answer will be the same. So that's pretty much the same situation that we utilized implicitly in Calculus 1, and now it is really crucial. We had to assume that it's path independent, and then we have our function defined in that kind of a very indirect manner. So like I said, for every point on the plane, say, there will be a path from A to B to that point, and that's almost stated, but I think I might want to impose an extra restriction just to keep it simple. So converse, I want to impose an extra restriction, meaning because what if I cannot, I'm implicitly assuming that I can get from point A to any other point within my domain, which might not be necessarily the case unless we require that domain to be path connected. Okay, so if Q is path connected, a path connected subset in Rn, also and suppose then F is a vector field with path independence. Then F is gradient. And we found the gradient in this kind of implicit way. It's continuous vector field just in case, so we can actually carry out integration. Okay, so as you can see, that allows us to really understand that that is really about the fundamental theorem now becomes more clearer that path independence of curves is identical to the vector field being gradient. Okay, so. And I guess what matters here then, the second part that I brought up here is that for gradient vector fields or for now path-independent vector fields, we notice that this is true. So along every closed path, we have integral equal to 0 because we can make just a round trip like this, and then we have to come back. Okay, so if we do come back of the curve, then this kind of trip supposed to be equivalent in as far as the integral is concerned to the trip that is what you just stayed home. So imagine this trip on one hand. On the other hand, the other trip is you stayed home like this. Okay, they should supposed to produce the same line integral. But if you stay home, your integral will be definitely 0. Right, so there is no work performed. So it means that whatever round trip you make under path-independent conditions, you will end up with 0 work. Okay, so that's another way to connect the two. Okay, so this is certainly deserves more discussion, but let's just take for granted that fact that gradient vector fields are path-independent and vice versa, all path-independent vector fields are gradient. Okay, but that's not enough because there are very few gradient vector fields, and then we are moving on to more complex. situation, and that is we're going back to the gradient test. The gradient test of the which is this of the that's in dimension 2. So we have to go down in dimensions. All of today's discussion has been so far about all gradient, all vector fields, or all dimensions rather, and this one is dimension 2. Okay, so in dimension 2 we have this condition that if violated also tells us that the vector field is not graded. The example is once again the rotation vector field. Okay, and then there are two. One of them related to each other. One is just plain rotation, which is you go faster as you move away from the origin. The other one you move slower as you move away from the origin. Both of them are not gradient, but the second one passes the gradient test. It satisfies this equality. Then we also, so that's the gradient test is right here. We also, this is a very convenient concept as you can see over here. So if we're talking about the gradient test, it is this expression has to be equal to 0, and there's a name for it. It's called the rotation, or rotor, the rotor of the vector field. Okay, so why is it a rotor is certainly worth discussing, and I think we just should examine that. Okay, so where is rotation and why it is important in the first place? So it is a tricky concept, so I want to go down to straight to discrete situation when everything is constant or almost constant. So once again, so the rotor is of a vector field PQ is QX minus PY. So you remember where it comes from, the partial derivatives of the two components, and they have to be equal if the vector field is a gradient. Okay, so let me refresh your memory here. So that vector field, if it happens to be gradient vector field, then these two, the components of that vector field, are the partial derivatives of a function, like this. Remember this diagram, right? So we're starting with the vector field, and then we're looking for its gradient, and we have found it by algebraic means recently, and just now we did it by integration. But that's the picture is here. So is there an f such that the p and q are the partial derivatives of that function? That's all fine, but then if you continue to differentiate with respect to xy, then the two mixed derivatives, this is p sub y and this is q sub x, have to be equal to each other according to Clause's theorem under continuous differentiability conditions. Okay, so that is where the rotor comes from. So that's all good and well, but the connection between rotation and gradient vector field has not been really established yet. So why is it even called rotation to begin with? It might get clear. So let's do that. Well, first of all, one thing that is clear that the rotation of a constant vector field, so rotor of a constant vector field, so PQ is equal to 0 when PQ are constant. Okay, so constant meaning like this. So it's the same vector throughout. Then what happens if you differentiate the constant function with respect to the two variables? You have just simply two zeros. So it will be 0 minus 0 is equal to 0. Okay, so the rotation of constant vector field is 0, so there is no rotation. It's very predictable. However, it also might mislead you into thinking that it has something to do with the actual rotation of vectors. It doesn't. Rotor is not about rotation of the vectors of the vector field. It is about whether or not that vector field can rotate something. Okay, so roughly speaking, so you have a stream, okay, but you are not studying the stream. You put an object in, let's say maybe a small ball, such as a ping pong ball, okay, and then you see, is it going to rotate? That's the question. You do not allow you're not allowed to leave. You put a pin in it, okay, and then the string will or will not rotate. Okay, so clearly when you have a constant vector, constant flow, perfect flow, the ball will not rotate. Okay, so under other circumstances, it will probably will rotate, but sometimes it's not, and so that's be investigated. Just we will do it quickly. So this is a trickier. So once again, it has nothing to do, rotor has nothing to do with rotation of the vector field. This is the example that is a standard example that easily can trip you up. There is no rotation. The vector field has no rotation period. So all the vectors of the vector field are in the same direction. Okay? So you would say there is no rotation, maybe there isn't, but the rotor is not zero. Do you see it?
It's going to be positive, is that right?
Yeah, the positive negative, it depends on the direction of your no, it's actually here. Well, if I put it here, the direction of, remember, counterclockwise is the positive direction. So if I put the ball here, will it rotate? Well, no, but what if I put it here? No, it will rotate. So the flow on one side of the ball will be slower than on the other. It's pretty much like lifting thing, lifting force of a. That's supposed to bring up an airplane, support the airplane, but the slower motion on one side and faster motion on the other side, that's what creates rotation, and the rotation will be, this one will be clockwise, and so in that sense it's negative, but if you put it over here, then it will rotate in both cases actually, they are both counterclockwise, they're negative, right? Yeah, so as you can see, it's in a way, if you think about what if there is it's like a cancellation of the flow on one side versus the other. So if there is no flow on one side, imagine this is a ball, and there is no flow here, like it's maybe resting on something, then the flow on the top will rotate, right? So if you have the difference of flows on two sides of the ball, then they cancel out each other unless something is left. So if there's a difference, then if there's no total cancellation, there will be something left to rotate the ball. Okay, so that it is a bit tricky. Another tricky part I wanted to warn you about is that we keep skipping between the force field and the flow field, and this one. And even though we're talking about work and we're talking about force field, this one I jump back to flow field, but really we're thinking of this flow not as a velocity field, but rather as a force field. So these are still forces. As far as the ball is concerned, the flow imposes force on it and try to rotate it. Okay, so we're not speaking of velocities. This is still about forces. So, and you certainly can think about forces with this property of physical nature, not necessarily coming from water. So, rotation not zero. If there is any kind of, in other words, there's on one side of the ball the flow is faster than the other. That's what creates rotation. Okay, there is a more example that will take us to furthermore from this. Is I'll probably will come back to this example again. So I want to make it as true as possible. So the ball may be even not a ball, maybe it is a square. Okay, and then on different sides of the ball, there is once again different flow. So suppose this is kind of a ball, and now I'll let me draw the my vectors. Say maybe like this. So this is my flow, and here I'll have horizontal maybe, and also horizontal. And let's go like this. Okay, so slightly more complicated. Do you think this will rotate by the flow?
When we say rotate, do we mean make a full circle or just any?
No, any. Will it push it a little bit, and it doesn't matter how much. No, the full circle. I mean, if you give it time, it will push it full circle, obviously. So once again, there's a pin. So this ball, square ball, is not going to flow away. So do you think there's rotation? Which way? Yeah, I think so. Okay, so let's confirm that. So this is the conjecture is that the rotation is counterclockwise. Once again, not the rotation of the vectors, even though you might argue that's what you see, but really it is a rotation of that ball in the middle that is in the flow. Okay, so let's compute the rotor. And once again, rotor is at the top, qx minus py. So we have to extract that information from this little picture. Okay, so let me try to do that. So, okay, so these are 1, 1, vector 1, 1. This is negative 1, 0, negative 1, 0, and this one is 0, negative 1. Okay, so there are only 4 values. So that differentiation that we see at the top really won't have to happen because there is no change and everything is incremental, so we'll just subtract. Okay, so in other words, we're talking about the difference quotient. That's all, even without the quotient, because how about I just say that this is 1 and then we're done, we're fine. So we don't have to divide. So squared 1 by 1. Okay, so let's see. Where is, so let me take the square again and let me write P. So this will be P. Okay, so P, what is P? Look at the top once again. It is our first x coordinate, x component of our vector field. So what is here? What do I write here for P? Negative 1. So I'm splitting my vector field into 2, P and Q, in order to compute the rotor separately. And I'm reading, for P, I will be reading the first component, for Q, the y component. So it will be negative 1. Over here it is 1, 0, and negative 1. For Q it will be 0, 1, negative 1, and 0. Right? Okay. So so now I'm doing P. Kind of a differentiation. Okay. So Px and Qy. So I'm sorry, P sub y. Okay, so I'm doing differentiation with respect to y. Can you tell me what it is?
Is it 0?
No, it is the change of p, and this is all the data we have. It is change of p with respect to y, the vertical direction. So, what is it?
Don't the one and the negative 1 cancel out? And,
No, you're looking at that would be x. Why?
oh.
Why? So negative 1 minus 0. Okay, so that will be our P1. Now Qx is, what's Qx?
Zero minus 1.
1 minus 0. Because we want to go, our x's are these, so always moving in the direction of y. It's almost literally the partial derivative, so we subtract the last value minus the previous value. So this one is equal to negative 1, and this is equal to 1. So then what is my rotor? It will be the difference of, once again, qx, as you can see, minus py. So it will be 1 minus negative 1. It is equal to 2. So 2, positive number, rotation, as we conjectured, is in the positive direction, in the counterclockwise direction. Okay? So, well, that's to begin with. We'll come back to this example, but actually, well, probably, let's make one more observation. and kind of long-term, long-reaching observation is what about line integrals? What about line integrals? Because I have my vector field right here, the in red, that's my vector field F. I can also see here a path. How about this is my path, a circular path. Okay? So forget about this part for a moment, everything about the rotor, and just look at the line integral. Along this integral, F, which is supposed to give me the work, over line integral of some kind. So integral over C, clockwise, counterclockwise, F dot dp. Okay, so the computation is very simple. We don't have to differentiate anything. Once again, the length are ones. So let's just compute work as we did a while ago. So going one at a time, starting point, how about I put starting point here, and we'll just look at the work. Okay, so there will be 4 terms, right, 4 stages. Each of them will compute the work. So, okay, what's the first stage? That one. This one. What's the work? Look at the arrows.
0, -1 dotted with 1, 0.
Maybe. Yeah, I mean, yes, but I think we can skip straight to the answer. The answer is 0, right? The work, the force is perpendicular to our path, so it does not contribute anything, so it will be 0. Okay? So this is work. And then the second one is vertical. Once again, lengths are ones. So what is the work along this path of that piece over there? The vector is 1, 1. We're moving in the direction 1, 0. So what is it?
1.
1. Okay. Now we're moving backwards to the left. Okay, what is it? 1, right? Right. So they are parallel. Okay. And the last one down.
0.
0. So the answer is 2. Well, naturally, we have 2 2's, and they're equal to each other, and it's not a coincidence. So we'll demonstrate that this is indeed a law of nature, sort of. That the line integral is equal to what? Now that's a good question. Will be what is it equal to? It appears to be equal to what is on the right. It appears to be equal to the rotor, the value of the rotor, but it's not really the value of the rotor as much as it is actually. Well, we'll see what it is equal to. It appears to be equal to simply the rotor of that point. Okay, but the reality is it's actually a double integral of the rotor, as we're going to see shortly. C bounds. It's called Green's theorem, and we're going to certainly spend some time thinking about it. So the proof is, of course, from the we got to justify it more than just this. Drawing such and such a conclusion, we carried out the whole thing only on we assume that the region itself, that region D over here, that's simply a rectangle. It is bounded by curve C, which is simply those 4 edges, and the force field was also very, very simple. Okay, so it's so trivial. So that's why we didn't have to do any differentiation or integration for that matter in order to match up these 2 quantities. Okay, and the procedure is fairly standard of how to extend this situation to the general situation when we have possibly continuously changing vector field, some weirdly shaped region. Okay, and the procedure is fairly simple, and the idea is first of all we got to start building a bigger set. a bigger region. So you start with two. You start with two rectangles. So we know that if squares, if we have for one square, we know this equation is satisfied. Okay, by the simple reason that that d is a simple square, so this integral is simply equal to the value of the rotor. Okay, so that's why it worked out so simply, because the original was so simple. Now we make one step away from this extremely simple situation. We have two. Okay, so for each of these, so this might be C1 and this is C2. And this is D1 and this is D2, and for each of them, this equality is satisfied. Okay, so what if we add them together? C1, D1, D1. Okay, so and then I have the second one, C2 F dP is equal to double integral D2 rotor F dA. Okay, so I have these two together. What do I get? Well, let's look at the right-hand side, which is simpler. What do we have on the right-hand side? Two double integrals over two adjacent regions. What do we do with them?
We break them up into their own integrals, and each has value 2.
No, we already have. I'm talking about one integral, the other integral. I'm adding them together. It will be one integral again. But it will be integral over what? Over the whole thing here. So it will be d1 union d2. All the same thing. So as you can see what's happening. What am I using here? I'm using, by the way, that's not a dot product. What am I using here is the additivity. Remember, the additivity of integrals is when the regions do not overlap too much, you can just add the integrals and merge them into one. That's exactly what I did. On the left, it's slightly more complicated, but, well, maybe you can guess what happens. So two integrals, and they're, can you guess what happens on left? How can I merge these two into one integral? So once again, C1 is this one, C2 is that one, and I put these two together, and once again, some kind of additivity kicks in, so it will be as if integral of C1 union C2, which is okay, so that's fine. The additivity applies to both double integral or line integral, so I'm using additivity twice. But this is just unsatisfactory answer. I say I can simplify this integral. Integration of my vector field, same thing, over these two curves. How can I simplify? I want to make a bigger picture for you. Okay, C1 is this, C1, and now this is also counterclockwise, C2. Okay? You see what's happening?
Yeah, the middle part is
Then
negated.
the middle part will be cancelled. Okay? So then the integral becomes over some curve C, and what is that curve C? So this part is cancelled. Why cancelled? Because look at it, it's the same integration of the same vector field in two opposite directions, along the exactly same curve in two opposite directions. So that's not the way they cancel out. The same exact curve, so it's not going to path independence or anything like that. It's exactly the same curve, and we're working in the opposite direction. So we know that's what what happens to the integrals. They cancel out. So then we're left with what is the curve C. once you remove these two parts, what do I get? They are actually quite nicely will merge into one. C1 and C2 turn into one big counterclockwise curve. Okay, so what is the point of this cancellation? The point is to come back to our original statement over here, and this is C. The statement was that the curve bounds the region, and it does. Okay, so this C bounds D1 union D2. Well, we could call D again. Okay, so adding an extra square to our situation does not change the result of our the formula. Does not change the formula. We still have the same formula. So the left-hand side, line integral along curve, closed curve. I probably should have done this a few times. So to emphasize the point that we're talking about closed curves. Okay, and secondly. And then in the meantime, on the right, we still have a double integral of the region bounded by that curve. Okay? So that procedure is just one step of the procedure. You can imagine that I could now add these squares more and more, and every time nothing is going to change, the formula remains the same. So like this. So I start with 1, and then I already added 1, and then I could add another one in any place that I want, like this. And then I could build from these little squares, I could build any shape that I want. Okay? And so then this is my region D made of squares. Okay? And so that's my region D. And then it has it is bounded by a curve like this, curve C. And then my statement of Green's theorem remains that the line integral along the curve close C, what is it, FdP is equal to double integral over D, the region that is bound. D is inside. Okay, so D is two-dimensional, C is a curve one-dimensional. So that's certainly to be remembered. Okay. So double integrals that we have talked about for a while ago rather, and for a while we have been talking about the line integrals, and they are connected to each other in this nice formula, Green's theorem. Okay, so it just take a while just to extract everything from this formula. What it means? It means a lot. So first of all, let's make it clear that it is. Let's ask the question: what if f is gradient? So what happens to the formula, Green's theorem, if our vector field is gradient? What's the order of a gradient vector field? 0. So the right-hand side is 0. So in other words, we are back to this discussion at the beginning of today's class. Is the along, this is true along any closed curve C. Okay, so in other words, and we know what it means. What's the other way to put it? Curve, closed curve integral is 0. What's another way to put it? F is path independent. So it is path independent, and so what it means that, generally speaking, we then conclude, as we have, that my line integral will be, in fact, not circular anymore. F dp is f of b minus f of a. So in other words, if we make this assumption, extra assumption put on our theorem, what we arrive to is the fundamental theorem. Fundamental theorem of calculus of gradient vector fields. Okay, so in other words, this little formula in fact contains the fundamental theorem. So it is, in other words, not just contains, it is a generalization of the fundamental theorem. Which means that it is the fundamental theorem. The fundamental theorem. So remember in the beginning I said that fundamental theorem we saw was a preliminary version. Well, it was. Now this is an actual version. Green's theorem. It is the actual fundamental theorem. And why? Because there is no restriction on the vector field itself. It does not have to be gradient anymore. Okay, so how much non-gradient it is in fact the term in the right hand side. It indicates how much non-gradient it is. Yeah, the clock is behind. Okay, so we'll just try to wrap it up in the remaining 2 days.